Welcome back to the course on textile finishing. Before we go further, let us see what did we do last time. We have learned that flame retardants are important because most of the textiles are flammable, polymers are flammable, and therefore, they do pose fire hazards and dangers to the life and property. Burning is a thermo-oxidative process which releases heat as the burning takes place, and therefore, this heat can go back and restart or initiate the degradation process. So, it can be fed back to the system, that is the polymer or the fiber that we are talking about. Combustion is an exothermic process, and during this, as we said, the heat will be released. The fire triangle also we learnt about, that the polymer burns, produces flammable products, they react with oxygen if oxygen is available, and then heat is released. And of course, we did talk about some of the strategies that you can adopt, so that this fire triangle can be broken. Generally, we did say that there are two basic mechanisms. One is called the solid phase or condensation mechanism, and the other is a vapor phase mechanisms. We did learn something about them. The aim of all these things, whichever kind of a compound that may be used, will be to somehow disrupt this fire triangle, right. So, today we will learn a little bit of the chemistry of some of the fire retardants and introduce various types of possible flame retardants. So, the condensation phase, as we are talking about, is basically related to formation of maybe a protective layer around the surface or the polymer or the area of the polymer which is burning. So, around that, if some protective layer could be created. So, the flame will not very directly go, it has to go through this protective layer, or they can work like a catalytic dehydration. Acids can be used, and that can alter the path of decomposition. That means, the way the pyrolysis was taking place, that may get changed, and therefore, this can happen through the catalytic dehydration. They may help in reducing the temperature of decomposition, because only at certain temperatures certain type of products are found which may be fire hazards in that sense. And so, if you reduce the temperature of degradation, decomposition, you may be able to save or restrict or retard the process of burning and degradation. Also, during this process of this alteration, they may reduce the formation of tar and gases. So, one of the type of compounds which are called the intumescent compounds or products, and this phenomena is called the intumescence. So, they are the ones, the types which actually try to create a boundary, and they create formation of large amount of char, and thereby reducing the diffusion of the oxygen or the flame coming close to that product. You may have at some stage or the other seen some such products. So, this compound is a mixture of a binder, and when this binder gets the heat because of the burning and so on and so forth, it will get softer and will start in some sense, let us say, melting, and the chemicals which are there, they will start reacting, they may start releasing gases. So, foam can be created. Now, this foam, if it is a carbonaceous product also, as the carbon keeps burning, then it will insulate the polymer from the heat. So, what happens is the hydrogen gets burned, so it is called the carbonization. The foam can then solidify and start insulating. I mean, the color of course is black, and generally it will be referred as char. So, we did talk about last time char to tar ratio and so on and so forth. So, you produce more char. You may have seen some products like a tablet of an intumescent mixture, which may be solid, and the moment you put certain amount of fire to this, it will start burning because that polymer is there, it starts burning. There are products which are inside, they will start burning, and suddenly a large volume would be created, which basically is a char, black, very soft material that remains, but the volume obviously is increased because it is foamed, it is foaming is taking place. Some of the interesting compounds that can be part of this type of a intumescent product can be one compound called the pentaerythritol, which is basically C5H12O4, and approximate structure is like this. So, you have 4 hydroxyl groups which are in a way connected to CH2OH, 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 and of course, in between you have a carbon there. So, there are other compounds like ammonium polyphosphate or melamine, which you know already, can also be there, which will start producing gases as they decompose themselves. And at the same time you have a binder which is becoming softer, and so in this so called melting mixture you have gases being formed and bubbles getting generated, and of course, they get out. During this process, of course, the hydrogen will also burn, and then you will finally have more of carbon, 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 and so that becomes a carbonaceous charry material. The binder, as we said, is vinyl acetate copolymer, can be other compounds also, but this is one of the common thing. The example you can look into is ethyl vinyl acetate, which is, as I say, copolymer. So, this is one which is going to be holding these compounds which can form gases and then foam, and as the carbon compound gets heated up, the hydrogen will slowly get out by hydrogen extraction methods and react in whichever way, and finally get out, and suddenly you have a large amount of foamy, charry compound all around. So, it stops. So, if you can apply these kinds of compound to any product, polymer, wood, cellulose, then it would by its own create such environment. There is another interesting product mix which people had been using for flame retardancy, borax and boric acid mixtures. All right. So, boric acid is H3BO3, which you are familiar with. This also acts like an acid and a flame retardant. The borax on the other hand is a sodium salt of borate, which is a complex compound. It is a very complex kind of compound. But more than that, all around this it can have approximately 8 molecules of water as a water of crystallization. They will be generally associated. So, whenever you keep an anhydrous material in the atmosphere, you will see that it will absorb a lot of water. So, once it absorbs water, so during the flaming, burning, this water will be released first. So, you can say one compound which is some molecular weight, it also got almost 8 molecules of water associated. Now, that also you can see will obviously one of the mechanism which was there, that if it degrades by itself and produces some compound which require for their, let us say, water getting into steam, require the heat, so the heat can be reduced. So, that is one part which is important. So, very simple methods like pad dry cure methods could be used. Curing actually is not required, pad dry, because no chemical reaction was expected. So, pad dry can be applied to cotton, viscose and such type of material, jute, and then if you have approximately 10%, 12% add on, it would give flame retardancy. It has been very successful. Anytime, anywhere, if you want, you can just mix them, just heat it a bit, the solution will be there and you can apply, dry, and this is okay. So, when it is a dried fabric, when subjected to flaming, it is going to retard the flame. You may see the glow in this case, but the major part of the degradation process will be stopped. But it is a temporary finish, because no chemical covalent bonding etc. reactions are expected in this. So, every time you wash, apply this also, and one can be safe. People can apply through pad dry, or you can have a spray and dry. But important thing you must note down here is that generally the amount of a flame retardant required to achieve a satisfactory retardancy is high. 10 to 12% we have written, sometimes can be more required also, based on how severe is the flaming condition. Unlike, for example, softening treatments, unlike, for example, grease resistant treatment, or even soil repellent with fluorocarbons, all of them require much less amount of material, much less amount of add-on. But for flaming, it is very severe and the burning conditions are severe, and so generally a higher add-on is required in flame retardants, of the flame retardants. So, now we talk about other mechanism which in a way is changing, altering the path of decomposition. This particular example that we are giving is based on the cellulose polymer based fiber fabrics, is the formation of levoglucosan. The levoglucosan is a product which is a tarry product which can form the gases, and so it has a ring structure which gets formed during the pyrolysis of carbohydrates such as cellulose and starch. Okay. So, this compound is in a way a dangerous compound, which is because it is a flammable product. It easily supports burning, supports creation of a flame. So, this for example is our general cellulose molecule, a carbohydrate in a way. So, when it burns, it can make a product like this, all right. It also is a product which is called the levoglucosan. So, this is levoglucosan. It is a bad product. So, if we do something in the cellulose burning process and if this is avoided, then we are altering the path of decomposition, path of pyrolysis. Okay. In this category, a good number of phosphorus based compounds are there which can do this alter the path of decomposition. So, one of the compounds which we will talk about which is the phosphorus based compound is phosphoric acid or ammonium phosphates. It promotes charring, interrupts the combustion process by promoting charring. That is one of the things. If it had reacted, for example, this is like cellulose phosphate, okay, this is cellulose phosphate. So, once you have done the reaction, let us say by a pad dry cure process using a phosphoric acid or an ammonium phosphate or ammonium polyphosphate and things like this, then on a finished structure you would have something like this. So, it is covalently bonded. So, it remains as a with the fabric. And the reason obviously is we want this to be more wash fast, okay, more durable. So, during this burning process, this compound will release phosphoric acid, which would help this charring process, which would help in catalytic dehydration. After the char is formed, you can say the oxygen supply can be cut off, and so the burning process can reduce, because during this process phosphoric acid gets released. And this is what we were talking about, alter the path of decomposition. And if you look at the burnt structure, you may get a char. Char may be, as we said, is very amorphous, soft, foamed up material, which could be, let us say, considered as a carbonaceous material. Carbonaceous material. So, mostly it is expected that it will be carbon only, and a carbon which could not become carbon monoxide or carbon dioxide, which also can become. If you go to very high temperatures, then the thing that will be left behind will not be carbonation material, also it may just become an ash in case there were inorganic compounds in it. If there were no inorganic compounds for whatever reason, then it may just vanish. So, everything can become a gas. There is another phenomena which people observed, and that is called, if the most of the phosphorus compounds like this phosphoric acids and polyphosphoric acids or polyphosphates were found to be good flame retarding agents. But they also noticed that if nitrogen compounds are also present along with it, then there is a PN synergism, that is phosphorus nitrogen synergism, and that obviously helps to retard the flaming process further. That is what the synergism is all about. So, if ammonium compounds are also present, like instead of phosphate you have ammonium phosphate, you have ammonium salts for example, or otherwise compounds like urea and other nitrogenous compound present along with it, then there is a possibility that release of inert gases like nitrogen, ammonia, etc., can take place. They help in inhibiting this chain reaction that is taking place. Remember, we said that if some such gases which by themselves do not burn, they can dilute the gaseous environment also. So, they can do things like this. So, if nitrogenous compounds are also present along with the phosphorus compound, the effect is better. Therefore, sometimes people do use compounds like urea while they are doing pad dry cure process. So, this is what is the takeaway, and we can always remember that this would help. So, as we mentioned before also, ammonium phosphate would finally get to the phosphate, ammonia will get released, it will become cellulose phosphate, phosphate will give phosphoric acid during this decomposition process. If that happens, then automatically the effect will be seen, the flame retardancy effect will be observed. So, one of the example also is like ammonium polyphosphate. So, you have lot of phosphate entities. Idea here is that how much phosphorus by itself can be attached, the more the better, that is how it says. And also in this particular compound you can see there is going to be the NH4 entities, they may remain associated, and because of that it is ammonium salt of a cellulose phosphate, let us say, which ultimately will release ammonia, then release phosphoric acid and get to the job. So, one interesting thing which people observed about the cellulose phosphate. Now, cellulose phosphate or ammonium salt of a cellulose phosphate, they are covalently bonded. Only the ammonium part is ionic, but the phosphate, which is the compound, is covalently bonded. So, one would expect the durability to be as high as one imagines till the covalent bond breaks, which we expect to break only during burning and not before. But there was an interesting observation, and that observation was that when you wash this fabric, the flame retardant finished fabric, the flame retardancy would start reducing, effectiveness would start decreasing, while they found that the cellulose phosphate was still intact. This covalent bond during this washing had not broken, and still the flame retardancy effect was reduced. The important thing is that if phosphorus is there, the glow was not there. So, in the borax case, we may find that mostly it is flame retardant, but the glow may be there. So, one important thing also was that if phosphorus compounds are also present in the cotton waste systems, the glow, which we said the temperature of the glowing was higher than the flaming, slow, but it can finish. The phosphorus compounds basically help making the carbon into carbon monoxide or carbon dioxide, and therefore, very easily the glow is reduced or inhibited. That is one important thing with the phosphorus compound. But I just mentioned before, the performance on laundering was reduced. Performance on laundering was reduced. And why did it happen? Before we talk about the remedy, we must say why this happened. One of the things which we found was that the ammonium salts or the ammonium ion was replaced by the calcium and magnesium ions, which we know are present in wash liquor because of the hardness, and this ion gets replaced by the magnesium and calcium ions. And if that happens, they found the performance is reduced while the compound is still intact. So, remember we talked about the sphere of influence and the time when these compounds are going to be available. If there is a delay, let us say in availability of phosphoric acid during burning, that delay will make sure that the most of the pyrolysis started and the action takes place later. It must take place quickly, it must take place as quickly as possible. While the ammonium salts were very effective, ammonia would immediately get released, phosphorus will then get released, phosphoric acid will get released, that means, and then the inhibition started quickly. But when the calcium magnesium salts were formed, it was found that the availability of this phosphoric acid was delayed because they would not get into gaseous forms, and because of that little delay, the compounds were less effective. That is why there is a term which we talked about in the classification semi-permanent, These type of reactions which were there were found to be deteriorating in performance, and therefore, they may not have lasted up to 15 laundries, and therefore, they said, well, these are semi-permanent type of finished products. Although remember, the covalent bond is still intact. Okay. So, what is the remedy? The remedy is for these compounds was that you treat with dilute, let us say acids like hydrochloric acid for example, and then neutralize by ammonium hydroxide. Then the ammonium salts will form again, and you will find that the flame retardancy is revived, right. If something like that happens, but obviously it is difficult for the user to do it. In the lab it can be obviously tested and you can check this out. So, an alternate story was built around different phosphorus compounds. One of the very successful phosphorus compounds is known as THPC, that is the tetrakis hydroxymethyl phosphonium chloride. This particular compound in a pad dry cure system along with urea or other nitrogenous compounds was very, very effective. And this did not have the problem of ion exchange. So, you have a chloride ion, and this group which we are referring to is this, which you are quite sure is hydroxymethyl, or you probably earlier know it as a methylol group. This compound is very effective and commercially a successful compound. At some stage, people wanted chlorine not to be there. So, if you replace chlorine with hydroxide, then this type of a compound was called THPOH. Approximately similar efficiencies were seen in this compound. So, that is one important as far as the phosphorus compounds are concerned. Some nitrogen, we said nitrogen compound by itself may not be very successful, but nitrogen plus phosphorus can be successful. So, there are some nitrogen phosphorus type of compound which you may have seen before, which was APO. We may have used this compound for cross linking purposes, but it can cross link. This is the group azididenyl group, which is this. Of course, it can cross link. So, it can attach a phosphorus to any polymeric compound which can react, like say cellulose itself. Reaction with amines can also take place. So, it will attach phosphorus and nitrogen together, and finally, we will see the effect of nitrogen as well as the phosphorus. So, they are very effective flame retardant compounds which can give you other properties like cross linking, etc. So, if somebody asks this question, well, after the flame, the fabric has been subject to flame, then what will happen to the crease recovery? I mean, it has no meaning. We never, as we said, design any material to be used after it has been subjected to flame. It is gone. Our aim is to protect life and property. So, most of these compounds, the phosphorus compounds, generally acted in the condensation phase. So, the other mechanism and therefore, the compound which will work in that phase, the other phase which is called the vapor phase, let us look at them now. So, during combustion, so free radicals get generated. So, polymer is there which will have hydrogen abstraction, and so you get free radical generated, and obviously they are very highly reactive species. Anything which is available close to them, let us say oxygen comes in contacts, they will start reacting, or they can react with anything else. So, this is what will keep on happening. So, if there is hydrogen has been released, because hydrogen may be present because of let us say this particular thing reacting by itself. So, hydrogen gas can be produced. Then you can have the oxygen which can also, which is being supplied, as we say, it is a thermo-oxidative process. So, oxygen is being supplied, and so oxygen can also get into oxygen radical, and if there is hydrogen available, it can create radicals which are hydroxyl radicals. They can again react with themselves, or they react with, let us say, this to make water. So, all such things will keep on happening during this combustion process. The hydrogen radical can react with oxygen to again produce this and another oxygen radical. You see, all this will keep on happening. If carbon monoxide is available, then it can become carbon dioxide, and again hydrogen radical is ready. So, these small entities of the hydroxyl based or hydrogen radicals will keep on getting generated and reacting with oxygen available, or go and react with whatever carbon compounds may be there to keep the reaction going till neither the polymer is available nor any carbon for that matter is available. It is all finished. So, there is no product, the flame anyway will go out, all right. But till the polymer is there, this will continue, this process will continue. If gaseous products are being formed, they will go into the environment, and this flame environment will be having all these kinds of various free radical reactions. So, one of the mechanisms in the vapor phase which operates is called the quenching of free radicals. Quenching of free radicals. Quenching means that this free radical which was available for further promoting various kinds of other free radical reactions can be quenched. So, there is a free radical which some other chemical comes and then reacts with this, which may not be flammable. So, this particular very reactive species becomes almost unreactive, that is called the quenching. So, inhibition of the flame means that there is an evolution of reactive species by degradation of the flame retardant. The degradation of the flame retardant. For example, halogen based compounds can do this kind of a job. For example, if this is a flame retardant which is halogen based flame retardant, can produce gases like halogen gas. If suppose this was a chloride compound, then it will be HCl. If it was a bromide compound, bromine based compound, then it will be an HBr, and so these type of gases will be produced, and these gases will by themselves are not flammable, okay, but they start participating in the quenching of the free radicals that have been generated during the combustion process. For example, if you have a polymer which had gone through this process of hydrogen abstraction and there was a polymer radical, let us say the polymer radical can react with the gas which is the HCl for that matter or HBr for that matter, can produce a halogen free radical, all right. If halogen free radical, not halogen free radical, but it is a halogen radical, all right, but a free radical means the radical, okay. So, this radical which is the halogen radical can combine with, let us say, another free radical which is hydrogen and can produce this gas back, or this gas which is there here can react with hydrogen to produce another free radical, and this can also react with OH to get H2O. That means the thing which are trying to quench are these type of things can be easily quenched, and so the flaming combustion reactions will retard. So, various types of bromine based compounds are very successful, and they were very successful for synthetic fibers like polyesters, nylons, and they could be introduced during the spinning process or they could be applied as finished, all right. So, whichever way, so you can make inherently flame retardant fibers because they are man-made fibers, or you can give a topical finish at a later stage. So, they were very popular, very effective flame retardants which would be working in the gaseous phase or the vapor phase, very effective compounds. So, brominated compounds instead of chlorinated compounds were generally used, and these compounds could be very effective. They help to break the fire triangle. So, the quenching takes place, further free radical reactions are inhibited and in the gas phase. The bromine interacts with the free radicals, as we have seen, to stop the chain reaction, which obviously leads to generation of flame. So, these brominated compounds, as we said, effective, they help in breaking the fire triangle, they stop the chemical reactions, and therefore, they intervene in the thermo-oxidative process and the tendency of the self sustenance of the fire. One of the example is tetrabromobisphenol A, all right. So, this is the group which is interesting. This is the group which will break off from here and make HBr. Now, these bromine could be attached on ortho para positions. So, here it is represented, they could be anywhere. So, different compounds will be generated as if the bromine is in ortho or para positions. So, irrespective of that, if bromine is available, it will work. Remember, there is no phosphorus here, they are still very effective because they are acting now in the gas phase. They are not going to change the burning behavior of, let us say, the polyester or nylons or any other synthetic material. What they will do is, once they have gone, some gases are coming and the flame, during the flaming and combustion process, whatever free radical reaction takes place, there these will work, very effective. We had already talked about the halogens. So, chlorine compounds have also been used as a flame retardant. You may have seen the electrical wires. Most of the electrical wires have a coating, whether copper or aluminum or whatever you have. This coating is PVC. What is PVC? It is a chlorine based hydrocarbon polymer, all right, and it acts exactly in the same mechanism, by the same vapor phase mechanism. Chlorine is going to get into the HCl and HCl will participate in the free radical mechanism by quenching. Okay. The other type of compounds are chlorinated waxes and so on and so forth. So, whenever chlorine or bromine are available, they are going to be doing the quenching of free radicals. There are some other inorganic compounds also which have been suggested, which can be very effective, like the aluminum, magnesium oxides, antimony oxides. So, these are important inorganic compounds. Hydrated means they contain water of crystallization. Antimony trioxide in conjunction with bromine, phosphorus or nitrogenous compounds can be used. Of course, they will do exactly same thing, which is slow down the decomposition process, release of inert gases that can interrupt the chain reaction, chemical chain reaction, which is the free radical reactions also. They can also help in creating a layer, flame resistant layer like these type of compounds, and reducing the release of the flammable gases. So, and if they are used, some of them as chlorinated paraffin waxes, the antimony compounds, or along with aluminum trichlorides and antimony trioxides, these type of compounds can be used. For example, the tantages, canvas which is used for tantages is coated with chlorinated waxes, if it is along with an antimony trioxide, acts as a water repellent, waterproofing agent if you fill it up completely to a certain extent, and also together with that flame. Antimony trioxide is very interesting compound, although by itself it cannot do any retardant function. But when it is used with halogenated compound like we talked about PVC, or we talked about the chlorinated waxes, then it becomes very, very effective, and that gives us synergistic flame retardancy. Let us see how it does. So, they can release HCl, and HCl you know can work in the gas phase. But if antimony compounds are present, it reacts with these also, like the HCl can react with the antimony oxide to generate compound like oxychloride, antimony oxychlorides, which at different temperatures, some reactions of this happen at lower temperatures at 250 degrees, the others will happen at 300 degrees centigrade. So, this oxychloride in certain proportions can form a gas which is antimony trichloride, which is a gas. All these are solid, solid material. This particular thing which you have used can also, which you have produced by in this previous reaction, can further react and produce SbCl3 molecule again. This can again further at higher temperatures can get converted to antimony oxide, which we had to start with, and gas. Now, remember, this is gas, it actually is gas, so it is going to be in the vapor form, is being produced. This gas, which is the antimony trichloride, is a effective flame retardant exactly in the same way as HCl, but because so much of this can be produced by the antimony itself, if it is present, then becomes very, very effective. So, in tantages, terpolines, along with waxy compounds, chlorinated waxy compounds, if you add antimony oxide, it can do flame retardant, water repellency, water proofing, and so on and so forth. So, interesting. So, what have we learned today? We have learned today chemistry of some of the flame retardants, and in the next class we will talk about some other issues related with the flame retardants and maybe flame retardant for some special fibers or flame retardancy of some special fibers that we will talk about. Okay, till then, enjoy. See you in the next class.